Good afternoon, and welcome to the Energy and Sustainability webinar series with the headquarters of the U.S. Army Corps of Engineers. This is Eric Mucklow, the Building Technology Program Manager. With us today we have Greg Stockton, President and Founder of Stockton Infrared Thermographic Services Incorporated. He's going to be presenting a presentation titled Infrared Thermal Imaging of Buildings and Infrastructures. Basically, he's going to talk to us about how infrared technology can be used to visualize problems in buildings or other issues such as water leaks, insulation quality, things like that. It'll cover thermodynamics basics and the uses of thermal imaging for facilities managers. Imagery and explanations include the building heat and air, roofs, interior and exterior walls, and infrastructure, including waterways and above ground and underground piping such as water supply, stormwater, sewer, steam, hot water, and chilled water. This is sponsored by the U.S. Army Corps of Engineers. Thank you all for joining us today. And we'll click over to Mr. Stockton's presentation and let him take it from there.
Greg Stockton, and I'm an infrared thermographer for about 30 years now. Now I want to go through some basic stuff about infrared thermography and get a good foundation for the presentation, and then go through some building issues and infrastructure issues. Infrared is just below visible light, meaning just below what you can see visually. And visible light is 400 to 700 nanometers, and you see it's broken down into colors. And so in the electromagnetic spectrum, ultra meaning above, ultra means higher than, and infra means lower than, and that's where it gets its name. And infrared, far infrared is called, is divided into short wave, mid wave, and long wave. Now most of the imaging equipment that you had 25 years ago was long wave, then the trend was mid wave, and now it's back to long wave again because of the invention of the microbolometer. Just a little bit of thermodynamics just to get us started good. Heat transfer happens by convection, radiation, and conduction. There's one thing that the universe is capable of doing, and that is taking energy, that the higher energy, and taking it to lower energy. So the world and the universe are always trying to equalize the amount of energy. So if you have more energy, then it's going to try to go by those three methods, convection, conduction, and radiation, to less energy. So imagine heat going to cold. So, you know, if you take your hand, you put it on a desk, and you take it away, you'll leave an infrared image of your hand because it's conducting the heat, which is warmer. Your hand is warmer than the desk. So it's conducting the heat from your hand to the desk. Convection, if you ever tried to solder something in the wind, you know how convective cooling really works. Radiation is the reason that we can see with infrared cameras, because the energy is going into hitting the detector at the speed of light, is hitting the detector, and it makes a signal that looks kind of like video. I tell you, let's get back to this slide for a second. Try an experiment. Hold your hand up against your face without touching it, close to your face, and then move it back away from your face. Do it a couple times, and your face will feel and your hand will feel warmer. And that's radiation. Not that your hand is hotter than your face, that your face is hotter than the wall. So you're blocking the radiation from your face hitting the colder wall. So think of it that way. You're always radiating energy. You're always, everything that is warmer is always trying to get cooler. That's a good basis for that. You know, a little history about thermography. When I started, we had to put argon and liquid nitrogen and whatnot in these cameras to get the superconductor to work. And now the new microbolometers operate at room temperature. The cameras are being made cheaper and cheaper because of the microbolometers. So whatever camera you bought a year ago will be at least 30% off this year. And there's all sorts of different brands and configurations of cameras. But there's something, if you're going to buy a camera, you need to think about a couple of things. One, the features that it has. And the second and more important is the detector specifications. With the features on the camera, you can see what I've written here is portability, ergonomics, ruggedness, how no software, there's no good, perfect infrared software, but get one that you can at least work with. You know, how much they cost, whether they can be upgraded or not, and what kind of technical support you can get along with training. Training is a very, very integral part of buying an infrared camera. As far as the detector specs, the type of detector and the wavelength of the detector are the most important. You have to have enough sensitivity to be able to see differences in temperature of the thing that you're looking at. If you're looking at a steel being poured out of a hot ladle, you don't need a whole lot of thermal sensitivity. But if you're looking at a building and trying to see a slight nuance of something that's going on inside the wall based on looking at the surface temperatures, you better have some very good sensitivity. Spatial resolution is probably the most important thing because most cameras now are fairly sensitive. The pixels, the elements in the camera, you have to have enough of them to be able to see what you're seeing in a wide enough angle. So I'm going to spend the next two slides talking about those two things. The sensitivity has to be good enough for whatever application you're looking at. This is looking at concrete inside of a block wall. And on the bottom, I can clearly see it. On the top, it's too fuzzy. It's too fuzzy. I can't really make any judgment. And with respect to the amount of pixels, if you're looking at this building right here, and you look in the bottom left corner, a 160 by 120 detector can see that. A 320 by 240 can see 4 times more, and a 640 by 480 can see 4 times more, and a megapixel can see 3 times more, and it goes on and on and on. So the answer to resolution is put a telescope on and take a lot of pictures. The pixels are important, especially if you're limited somehow in the way you're doing seeing the image. Now let's talk about applications. There's just unbelievable number of applications for infrared. Traditionally, electrical switchgear was checked. A little before that, but not very well done, was building thermography. Back in the 70s and 80s, you might remember seeing an infrared picture of a tobacco barn or an infrared picture of a house. These were very homely images, I can tell you. And as the capability of the detectors comes better and better and better, we get better and better images, and we get more people because of the economies of scale. We get more and more people out doing infrared thermography. So let's talk about buildings and infrastructure. First, buildings, and the first part of buildings is building heat and air. This is an oblique infrared image of a building. You can see the steam leak in the sidewalk in the foreground of the image. And you can see there's warm walls on the walls facing us in the front and the left-hand side. And you can see little red spots. You can make some judgments actually about what's going on. The key here is, and this is super duper important for everything, that when you're looking at quality of something, we're with infrared thermography looking at surface temperatures. Surface temperatures. We don't see inside buildings. We see the impact from whatever's going on in the building and the quality of the should be homogeneous surface on the outside. Where we don't see homogeneous surface, we know something else is going on. So I'll come back to this in a minute when we start looking at other things, but the point being that the quality of things that you see is based on three ways to look at it. One, I put heat onto an object and I watch it warm up. Two, I put heat onto an object and I watch it cool down. And three, I put heat inside of an object or on the other side of the wall or whatever I'm looking at, and I watch it come through. Now, those are the three things you can see with passive infrared. If you have an electrical switch and it's got a loose connection, it's going to generate its own heat. All right, so let's go down to another couple of pictures, oblique images. Again, aerial oblique imaging of the sides of buildings has its limitations. It's great if you want to get a general idea of what's going on. It's not the end all. You need to go to the inside of a building to do a proper infrared survey. Now, you can get a good idea of what's going on, and you can get a good qualitative idea of what's going on by flying around in circles and looking at buildings, or standing on the ground and looking at buildings. But you need to go in, and not only do you need to go in, you need to be able to control the air. Another image here where we're looking at buildings, and you can see that if you look in the foreground, you can see that people got their windows open. Obviously, that's a problem. And this is a little better view of it. If you see the two walls, you can see which ones are open, which ones are hot, which ones are unoccupied. But again, there is a very big limitation on what you can do with infrared thermography from the outside of a building. Another infrared image, and you can see this definitely has some problems. Another image where we're looking at very low angle, and we can see that on the front there and all the way around the side there is definitely some much more heat loss than on the other part. And when you look at a building late at night and in the winter, and you see heat on the surfaces of the building that's warmer than the glass, because glass is a pretty miserable insulator, then you know you got problems. You can do 3D imaging of buildings. It's possible. It's much more expensive than just doing regular infrared, but some buildings warrant spending a little bit more money on for one reason or the other. I'm showing this picture to show what too early in the night looks like. If you notice, and I'll see if I can take this green arrow and move it around. If you notice right here, there's a lot of heat. This is a wall that's just received the sun, and you can see over here as well. And there's a line right here, and this is a telltale sign that the sun has come off. The sun has been shining on this wall longer, because just about no way could you have a diagonal heat loss in a building. So this is done too early in the night. Put this over here. And it's just another color palette of the same thing. All right, so there's a document that the U.S. Army Corps of Engineers created called Air Leakage Test Protocol for measuring air leakage in buildings. Great document, and it's got this best use is in new buildings. The bad news is, guys and girls, fixing buildings that are broken, that are old, there's almost no payback to it. It costs, your payback in energy savings is measured in decades on buildings where you have to go in and do something, put 2 inches of insulation in a giant building. It's just not feasible. Replace all the windows. Replace all the window frames. Completely rebuild the HVAC system. It just doesn't have any good payback. So the idea is to commission a building once it's built. Commission it, make it sure it's in good place, and then come back and retest it every so often. Now here's some example pictures of buildings undergoing air leakage testing. Now this is a summer night. There's air conditioning in the building. It's all glass. And if you notice the little dark marks, the little shapes, those are air leaking out of the building at the point where the interstitial space is. They're using the interstitial space as a return air. It is way overpressured, and it's blowing cold air out of the building like a sieve. This is a VA hospital. Old building. Tremendous amount of per square foot cost for heating and cooling. You can see with an infrared camera, you can see the obvious that nobody else can really see. They got uninsulated steam pipes in the wall, as shown on this right-hand side picture. They got vents blowing superheated air out. They got windows open. All sorts of things. A typical infrared image of a building where the air is leaking out, and it has a very specific pattern. Actually, if you notice the pattern in that little inset picture, kind of wavy pattern, that is air blowing out. So we have an infrared image here of before a pressurization and after a pressurization. Even before, you can see that the building has heat loss, but it's only about a half an hour difference in time. What we did, I will explain in this next couple of slides how we created these images and what happened. So this is a little oblique picture on the left on the right, what we're doing here is we turn on about half of the RTUs in the building and ran them in full economizer, zip screwed shut the dampers so that they couldn't blow the air back out. So we pressurized the building, and you can see the rate of pressurization over here at about 25 Pascal, which is, you know, a canary can barely feel that. But it looks like the building is just completely leaking. The whole roof area is completely leaking. And here's a little diagram on the bottom right that shows how the RTUs are. So again, we zip screwed shut the damper so it couldn't exhaust. And this is another picture where you can, you know, see how much heat loss there is. Now, even before pressurization, you can see every board of insulation in this building. And on the right, you can see every board of the insulation in the building is leaking air, like a sieve. So the fix is to put down some kind of a barrier to keep that much air from leaking out, and to run the building at a very, very slight positive pressure. I mean, we find a lot of moisture problems in buildings. Almost every big building you can stop from having a moisture problem by just running positive pressure. Again, this is a picture from underneath where you can see that same kind of pattern. And of course, all the doors leak, and especially the garage door type of doors leak. This is a retail building. Loading docks. This is a building in the desert. It's during the summer, during the day, right after dark actually, but you can still light. And you can see just how much cold is leaking out of this building. Hotels hotels inherently have problems because they, by and large, even if they have a centralized system, they tend to have different amounts of air pressure in the hallways, different amount of air pressure in the rooms, and different temperatures as well. So the humidity changes a lot. Of course, you got the other problems, which are, you know, bad construction. We see two kinds of problems, not in hotels, but every kind of building. We see with infrared, we see design flaws and construction defects. Design flaws and construction defects. Those are the things that really infrared is brilliant at finding. Here's just a big office building where you can see, you know, obviously if you've got a difference in temperature, there's some problem. This is a huge convention center, and as you can see from the dark spots, the insulation's not up against the sheetrock right, or it's got a little air leak, or something's going on with many of these nice job guys. Somebody looks like they took like a deck of cards and threw it out. These are R19 bats that are supposed to be installed in the drop ceiling of this building. This is a heated space above. This is a construction defect. A lot of times the fix of people that are, when people are complaining, like especially very old people, in nursing homes and places. They're sitting down in the coldest part because the air is stratified. They're sitting down in the coldest part of the building. So if you just blow the air around good, you'll end that problem. You always see missing insulation whenever fiberglass bats appear. Fiberglass is a particularly bad insulation given its low R factor per inch, but it's an easy installation, and it still gets messed up quite a bit. These are just some random images of heat loss and the kind of things we see. Yes, you can see every nail and every stud. And I just threw in a couple of masonry buildings because I wanted to show, you may have, I mean, everybody's got block walls, brick walls, and stucco buildings. So this is a visual image of a retail building. And in this picture, you can see three conditions with an infrared camera. You can see the grouted cells, you can see the empty cells, and you can see the insulated cells. The insulated cells are darker because they're keeping the heat bouncing back and forth. The empty cells are letting the heat pass through easier, and the grouted cells, because this picture was taken about about 2 or 3 hours after sunlight or sunset, you can see the concrete that is the solid grouted areas. This is a great quality control for a construction site. You can see, you can't see the rebar, but you can see the grouted cells. And this is a daytime infrared picture where, again, you're seeing this, they use urea formaldehyde. This is a urea formaldehyde foam, and you can see the little spot places where, it goes up, looks like a bar graph. It's okay to not insulate it above the roof line. About the midpoint, well, about 6 feet above the midpoint of this building is the roof line, because there's a parapet wall above. So this is not a problem. It's just showing that you can see it. And finally, stucco. Remember the part where I was just saying earlier, you hit it with heat, you watch it warm up. You hit it with heat, you watch it cool down, or you put heat inside and watch the heat pass through. So if you have stucco, I don't care what kind of stucco. If you have stucco, it's on in layers. And it should be one contiguous, homogeneous piece that is stuck together with all its layers. So it should heat up and cool down exactly at the same rate everywhere. And as you can see from this picture, where the little dark spots, the little cracked little areas and little dark areas in this picture, and it's all the way down, it's the whole building is like this. This has the potential to break pieces off and have them fall down and hit people in the head while they're sitting at the pool. So it turned out in this building particularly that the stucco layers were put on in the wrong order, and every bit of stucco was taken off of this building and one beside it. Okay, so now I want to take a little bit of time to talk about building roof moisture. Leakage into buildings is not what we do. We do, infrared thermographers look for entrained moisture contamination. So yeah, when something leaks water in, it's going through the flashing, it's leaking. Some of it will be absorbed into the insulation if it's an absorbable insulation, and some won't. And whatever makes it pass. The purpose of a roof is to keep the water out of the building. So the roof is sacrificial to the building. So you want to put a kind of, if you're designers out there, you want to put a kind of insulation in the roof that absorbs water so it doesn't go down into the building. And if it absorbs water, then you can see it with infrared. And I'm going to spend a few slides here talking about why infrared is so superior to every other type of testing. The obvious problem with destructive testing is you're destroying the building. So the way to do this, and it's very good and very accurate, is pin type destructive. Sticking a hole in the roof measures the resistance across the two pins. All right, so then there's core sampling, which is great for verification. And there's non-destructive testing. The three devices are capacitance meters, nuclear meters. The capacitance meters basically are measuring the difference in the dielectric constant. The nuclear gauges are counting slowed neutrons. The problem with meter surveys is you have to extrapolate, because you're not taking a meter reading every 2 inches. So your sample is very, very tiny. With infrared, your sample is huge. And I'll demonstrate what I mean on a picture here. There's a roof. There's an infrared picture of a roof. There's an infrared an overlay of a CAD of the wet area. And if you notice, this is 5,000 square foot roof section, of which there are 80 square feet of wet insulation, 5 spots found with infrared. If you put a grid and put it at 20 by 20 or 10 by 10, you don't even hit any of the water. You have to put it at a 5 by 5 grid to see one of these spots, the big one. So the point is that meter surveys only prove that a roof is shot. It doesn't find and delineate water. That is why infrared is so valuable for roofs. And again, not to beat it to death, but putting plastic cellular foams down on roofs without a sacrificial layer of something that absorbs water is bad. You need to put something that absorbs water in it, because it leaks right directly into the building. So the point about infrared is that you're getting 100% of the roof surface covered. Again, infrared doesn't work on every kind of roof. And I see some of my slides are destroyed here. Let me go over a couple of things about roof moisture surveying. Roof moisture surveying with infrared is based on pattern recognition. The wet substrates have a higher mass and therefore a higher thermal conductivity and specific heat. The specific heat capacity of a wet piece of insulation is a lot higher than that of a dry functioning substrate. And the graph is just like the graph on the stucco buildings and a lot of things that we look at. Basically, it shows that twice a day the temperatures flip between the higher mass and the lower mass areas. So we have to do our plan and plan to be at on the roof at the right time. So as you can see from this time temperature plot, wet insulation heats up and stays hotter longer. in that window of uneven heat dissipation, we do our work. A couple of methods for doing infrared under roof, and that's looking up. And most of the time you want to do these when you're looking at a big warehouse or something with vinyl back fiberglass in between the purlins. The way you do that is you go in the morning when the water that's stuck in the fiberglass, and it doesn't always bulge that big. Well, when it's stuck in the fiberglass, and in the morning the heat's going to come through the roof and start going in, and it'll take longer for it to warm up that cooled water from the night. So that's how you do that. Same kind of picture right here. You're looking for the heat's coming through, and you're seeing the little black cold spots. On roof, the most popular, by far the most popular way to do infrared is basically you wait till it gets to be night, you wait for the substrate to cool off, and it leaves these other amoeba-shaped areas and whatnot, and then you take a paint can and you mark the roof where it's wet. And these are just some infrared pictures of on-roof surveying. As you can see, some of these roofs are wasted, but most roofs, 99.9% of the roofs that we survey, and we survey ones that are bad normally, or at least the people are complaining about, most roofs are dry almost completely. Most of the time, if you tear off the roof, you're throwing away perfectly good insulation and perfectly good money. As you can see from this picture, you can also see the fasteners in the roof. So it's a good quality control. Again, you can see the fasteners in this picture. This is a roof that's been repaired on the edge, but now it's completely wet. Elevated is great. It gives you a great picture. We like doing hospitals elevated because you can stand up on the hospital roof and look down, and you're relatively close to it, so you get really good resolution. And then you can get a guy down on the roof, and you take a laser pointer and a reticle on the camera and have them mark it out. Just another elevated picture. Then there's the aerial, which is used for a lot of different purposes. Aerial is great because you're getting a straight down, perfectly straight down image, and you can draw CAD drawings of all this. So it's very, very high resolution now. This is about a 4-inch thermal resolution on this picture right here. Another similar picture. Again, the sun beats down all day into the roofs and the roof substrate and warms it up. You take away the sun. The areas that are dry cool off. Leaves the wet spots. And then you turn them into CAD drawings. It makes a marvelous bid document. The CAD drawings, I mean. But, this is a roof that it's an EPDM. It's got multiple layers. And I'll just flip back and forth for a second here. But if you notice, there's places in the infrared image that are much brighter than these other spots. They're both gray, but they're both bright. And you can see, these are patches. This is what, I'm sorry, let me get my pointer. Come on, you. All right. This and the bright areas that are this bright or brighter are water that's in the top layer of insulation that's wet. This is a patch right here, and then inside the patch you have water there. So you've got water inside old roofs, and then you've got again water inside the You got water in multiple layers on the roof. Like I said, the bid document that you want is something that looks like this, a CAD drawing. A CAD drawing of a roof, when you can see the wet spots. Most of the time, the roofing people don't really care what kind of fancy-dancy camera you got or anything else. They just want to know where the water is. And an overlay of a nice high-res photo.
Okay, if you could maybe pick it up and go a little while longer, then maybe at 10 till we'll take questions.
Exactly how many square feet it is. That is a document they love. So it's the 42 after the hour, so I'm talking to the host, so tell me how much more time I have, and I'll adjust my speed.
Okay, if you could maybe pick it up and go a little while longer, then maybe at 10 till we'll take questions.
Okay, great. All right, so just a couple of things about moisture. When you take water and you put it onto a surface, it is just cold. It's evaporating, and it looks to an infrared camera to be very, very cold. This is like the boy with the, don't pull out the nail out of your heart if you fall on it, because this rusted away over a course of a couple of years. It was just a nail that was put in during construction. It caused this building to be torn down. Yeah, one nail, one screw. We don't have time to really go into detail on interior moisture, but to say that sometimes you have to crawl around in attics and find the source of a problem by finding your way back to the source. Anything, when you have moisture in buildings, you've got mold in the air. Let's face it, mold's everywhere. So if you get conditions that are good for mold to grow, it will grow.
Oh, Greg.
And this is a perfect situation. You have warm, moist
buildings. You want to jump ahead to the infrastructure with the steam pipes and stuff and touch on that before we get to questions?
Water in surfaces, building surfaces such as sheetrock, acoustical tiles, pipes, pipe insulation, very, very easy. This is,
okay.
Yes?
You want to jump ahead to the infrastructure with the steam pipes and stuff and touch on that before we get to questions?
Certainly. So this is basically looking at infrastructure now. This is thermal mapping. Now, thermal mapping is flying back and forth through a city and seeing, or an area, and seeing what's going on. Basically, you're mowing the grass. This is a forest fire. This is Centralia, Pennsylvania's coal fire that's been going for 30 years, which started down here in the bottom of this picture. Landfill fires, leaky storm drains. Anytime you have water that bubbles out of the ground and goes across the ground and into water, it's going to be a warmer temperature, especially in the wintertime. It's going to be a warmer temperature than the surface, so you can see it. That's a power plant cooling tower discharge. Photovoltaics, looking at these you do during the day. One of the few things you do during the day. Again, this is an industrial complex, and we're basically looking. The idea here is you're mapping an area looking for anomalies. So this is a city. This is an infrared image of a city. There's the steam system. and this is a grid set up to be able to divide reports into little chunks. The idea there. Again, resolution makes a lot of difference. This is 30-inch. I'm just going to zoom through these. This is 30-inch. Look at the bottom left, and you'll see an arrow, and you'll see a little tiny little problem, and we're going to just completely zoom in on it. So it's 30 inches. This is 24 inches. Remember, GRE is the ground resolution element, or the size of a pixel on the ground. This is 18, 12. Now, with 12, you're starting to be able to see a lot of stuff here. You see what's going on. This is 6-inch. Good enough for roofs. And finally, 3-inch. And that you can see every detail now. Doing military bases, they have a lot of they got the same infrastructure as everybody. They got buildings, they got storm drain systems, they got water mains, they got steam lines. Just to concentrate on the steam, this is where you have above the ground and you have below ground direct bury steam pipes. And they're clearly seen in the infrared. The trick is to make sure that the steam line is turned on. Because if it's turned off, you're not going to see anything. So we like to do steam in the winter, because not because of what you think, which is that it's colder. The delta T doesn't make that much difference, because steam lines in the summer are great. It's the trees leaving that's our biggest headache for not doing steam surveys during the summer. Now, this is what a steam leak looks like. A leak, this leak is $30,000 a year, and it's the size of a pencil lead leaking. This is really tremendous savings from finding the leaks. You know, when it comes again to finding areas that have less insulation or deteriorated insulation on the steam line itself, there's a lot slower payback because you got a bigger investment to fix it. But steam leaks are no brainer. Find them and fix them. This is
it's 10 till the hour. Basically, I've opened up the Q&A block on the right-hand side of the screen.
This is a chill water line.
If anybody has any questions, if they could type them into the text window at the very bottom of that Q&A block, and enter them there, they'll show up to me. They won't show up to anybody else. And I'll basically consolidate any redundant questions, and I'll read the questions to Mr. Stockton to answer for the recording. Basically, I've opened up the Q&A block. But thank you, Mr. Stockton, also for your presentation. A lot of really good pictures there. I wish we had enough time to go over some of the ones we skipped, but we'll hopefully continue on with this. Let's see. Eric asks, can IR be used for sinkhole detection and underground electrical communication piping? But thank you, Mr. Stockton, also for your presentation. A lot of really good pictures there. I wish we had enough time to go over some of the ones we skipped, but we'll hopefully continue on with this. Let's see. Eric asks, can IR be used for sinkhole detection and underground electrical communication piping?
I'd say no and no, and here's why. There are better technologies for both. Sinkholes, you have if you're looking at a small area, a sinkhole's relatively easy to find, especially if it's about to cave in. But I have gone to known places that have sinkholes, and they're just so spread out. You're talking about huge area that you'd have to do. Now, it's
okay. We have another one here.
Like a highway.
I know you're not going to answer questions about contract services and things, but you mentioned that the cameras on the market are getting cheaper and cheaper and better than they were in the past. About what price range are we looking at as the lowest price range for a consumer or somebody to get a decent IR camera? Okay, we have another one here. I know you're not going to answer questions about contract services and things, but you mentioned that the cameras on the market were getting cheaper and cheaper and better than they were in the past. About what price range are we looking at as the lowest price range for a consumer or somebody to get a decent IR camera?
Well, the word decent is kind of loaded. The problem is that if you get a camera, if you go out and spend a couple of $1,000s and you get a camera that can see water in a ceiling, then when you have to do something that's hard, you are going to be limited by the capability of the camera. I think it would be better to get something about 50 millikelvin sensitivity and about 320 by 240 as a minimum kind of camera. And that's going to be probably in the $5,000 to $6,000, $7,000 range. But that doesn't make you an infrared thermographer. The point being that you should set aside 20% of whatever you're spending on the camera at least, and maybe more if you're buying a really cheap one, to get some training, because it's not as straightforward as it seems sometimes. A lot of times you can go out
and next from Fort Bragg, I know you covered mentioned the steam leak that was $30,000 a year that was fixed. I imagine that had a really good payback. What typical payback do you see for imaging on campus settings, such as military bases? Have you had in your experience? Or what should we expect? Okay, and next from Fort Bragg, I know you covered mentioned the steam leak that was $30,000 a year that was fixed. I imagine that had a really good payback. What typical payback do you see for imaging on campus settings, such as military bases? Have you had in your experience? What should we expect?
If you've got an old infrastructure, you've got leaks. If you got a hot water loop and you can measure everything really good, you can tell about what your leak is. But you can't tell the difference between steam or anything. You really can't. If you know you have loss, and everybody does, you can't tell how much of it is a leak and how much of it is just bad old piping. So if you got really bad old pipes, you're going to have to eat it, because the replacing them just costs a fortune. But if you get an infrared survey done, you will find the leaks, and those have got to be fixed. There's no question about them. And we always find, on the size of a typical college campus, we find an average of between 1 and 2 leaks. Leaks, not bad lines. Then you have the whole thing about boiling steam, boiling manholes, which you guys published an article about it, I think, at the U.S. Army Corps of Engineers. But with the manholes, if you have water, and especially if it's a swampy area like Fort Bragg, probably, you're going to have piping in the ground, and you're going to have water that is in and are surrounding the pipe. So you've got
now when you're doing the thermal imaging testing and pressurizing a building, or not, I guess, according to the question, what is done with the air conditioning system? Is it left running, or are the settings changed, or what do they do there?
No, I'd say that always. I have seen some pretty pristine systems, but they're far and few between.
Okay. Now, when you're doing the thermal imaging testing, pressurizing a building, or not, I guess, according to the question, What is done with the air conditioning system? Is it left running, or the settings changed, or what do they do there?
Well, typically, you know, there's two methods, and that document, the air tightness document, the test protocol, explains how to pressurize the building using blower doors most of the time. But you can use the building controls. Basically, what you want to do is what we did at that hardware store. We stop the flow out of the building by putting it in full economizer and bringing the air in, but not letting it come back out. And the only place the air could go was out the leaks. So then you can, that's a pretty simple operation. I know in some buildings it's not. I remember when we were doing testing at some VA hospitals.
I think I might have lost audio. Okay, well, it looks like our host may have been knocked off here. Not sure how that happened. Probably we've been having some slow network issues today. Hopefully he'll come back on. If he doesn't, then we had a couple more questions that maybe I can address as best I can. Can IR find mold in buildings? Mold is typically an issue of moisture, of water presence in a building, as well as having the right temperature conditions and a food source such as cellulose, wood, paper, things like that. So I'd imagine that when you can find mold, where you can find water, you can find mold. If there's very little water enough to cause a mold issue, I'm not sure if an IR camera could find it, but imagine that wherever you had these moisture issues that he outlined, where the water was visible, they probably also had mold issues if they had cellulose or mold food type materials. And one was we'll have to ask him about whether the time of day in a hot climate like Hawaii was better for the early evening or early morning before sunrise, or a few hours after sunset. He'll have to answer that one for us. Somebody says, this is a question for myself, is IR testing of the building envelope going to be a requirement? He's coming back now. Basically in our requirements we will have, we're putting out an ECB that won't change the requirements, but it'll give guidance on how to conduct testing, and it'll also include that paper that he mentioned earlier on the testing protocols and things. I would expect it for large buildings that it would be required. It just might not be for something very small, but we're definitely leaning in that direction. So let's see if we can't get him promoted to presenter. Make presenter. Okay, and let's see here. Greg, are you back with us?
Yes, I heard.
There you are.
I could hear, but the mold question, you cannot find mold with an infrared camera. It does not make a exothermic reaction strong enough for anybody to be able to find it with an infrared camera. As you correctly pointed out, though, where you have moisture is where mold is. So the direct question, it takes a microbiologist to find mold. But you find moisture with the infrared camera, and you'll find mold wherever you find moisture. Now, the question from in Hawaii, what was that again?
Yes. Yes, basically, when you're doing thermal imaging in Hawaii, what time of day would be the best time to do thermal imaging on a building? Early in the morning before sunrise, or a few hours after sunset, or something else?
You just want to have a delta T as large as possible. And by the way, I volunteered to go to Hawaii. But you want the largest delta T that you can get between the inside and outside. You know, if it's 80 degrees outside and it's 76 degrees inside, you're going to have a pretty miserable survey. Now, you need a more sensitive camera to be able to do that kind of work. So I recommend to the man or the lady in Hawaii that they take that into consideration when buying an infrared camera. Get one that has very, very low sensitivity, like 25 millikelvin, because you're going to deal with it when you're looking at buildings in Hawaii, I'm sure, because you don't get the extremes like you do in the Northeast and the Midwest and the rest of the country.
Okay, it's a couple of minutes after the hour, so I'll take one final question here, which is there a professional certification for thermographers?
Do we have another hour? Because that's how long. I'll give you the short answer. There is certification companies that do certification. So there's like, I don't know, 6 or 8 or 10 of them and with about 3 of them being the main ones that have certification courses that certify you as a thermographer. However, it's not like a CPA. You know, in a CPA, the state gives them the test, and they become a certified public accountant. But a certified infrared thermographer is actually, whereas it does hold some water in court, I know that. Being a certified infrared thermographer is basically going to a training class for certification, and there's 3 levels. There's level 1, which is all about qualitative thermography. In other words, not about measuring temperatures. And then level 2 is about measuring temperatures, and level 3 is about program development. So it's a great idea to get certified as soon as you get an infrared camera, so you don't start making a bunch of mistakes and giving people the wrong impressions.
Okay, well, it sounds like something we'll be looking for. It is always a challenge when there are multiple entities certifying the different standards and things out there of what we can specify in contracts, but we'll look to see if we can address that issue at headquarters. And basically, I want to thank Mr. Stockton again for his presentation. This has been recorded, and we will be uploading it to YouTube and our sustainability channel at some point, probably within the next week. And it'll be available for those who missed it. We will have the quiz. Every few sessions we have a quiz that you can download and take and submit. And if you pass it, get the continuing education credits for people who need to get those for their professional certifications. So again, thank you very much, and I will stop the recording now. And everyone, have a nice evening.
Okay, have a great day.